Hello everyone. We are here to present our project on the topic image generation using pixel CNN, pixel RNN, variational autoencoders, and GANs. In this project, we will be benchmarking the performance of the different generative models over the different data sets. There are a lot of generative models, and some models have an advantage over other models. Let's look at the advantages of different generative models. Advantages of autoregressive models over GANs. Autoregressive models provide a way to calculate likelihood. They return the explicit probability densities, which is not present in case of GANs, making it straightforward to apply it in domains such as compression, probabilistic planning, and exploration. We also find that the training in case of autoregressive models is much more stable than compared to GANs. This is because the training of GAN requires finding the Nash equilibrium. Since there is no algorithm present which does this, training a GAN is unstable as compared to pixel RNN or pixel CNN. Also, autoregressive models work in case of both discrete and continuous data. It is hard to learn to generate discrete data for GANs like text, but autoregressive models work for both discrete and continuous data. Let us look at the advantages of GANs over autoregressive models and variational autoencoders. So one of the major advantage of GAN using GAN is that the quality of image produced is of high quality and high resolution images. This is because of the development of advanced network structure and high scale training. Also, the images generated using GANs are much more sharp as compared to VAEs. This is because the generated samples from VAEs are blurred because of injected noise and imperfect reconstruction. Next.
Now moving on to datasets. So we made use of three datasets for our analysis. The first dataset was CIFAR10. So this is a labeled subset of 80 million tiny image dataset. It consists of mutually exclusive classes like automobiles, birds, cats, trucks, etc. Training image generation on this dataset will help us to create synthetic datasets of any of the included classes for further training purposes. Second dataset was Abstract Art Gallery. This dataset contains about 2,782 abstract art images scraped from wikiart.org. This data can be used to build generative models in order to generate synthetic images of abstract art. The third one was LSUN Bedroom. So LSUN Bedroom classification dataset contains 10 scene categories such as dining rooms, bedrooms, kitchens, outdoor church, and so on. We have used the LSUN Bedroom dataset for our analysis. Next. So the next step was data pre-processing. Data pre-processing steps were mainly done on the abstract art gallery dataset in the following two steps. The first step was frame removal. So we made a Python script to look for wooden frames around the images and remove those frames. Second step was resizing the images to 1024 into 1024 pixels. LSUN Bedroom dataset and CIFAR10 dataset needed no major data pre-processing.
So here we have a short comparison between the model architectures. Starting with the first, variational autoencoder. Variational autoencoder consists of setting an encoder and a decoder as neural networks to learn the best encoding and decoding scheme using an iterative optimization process. At each iteration, we feed the autoencoder architecture with some data. We compare the encoded-decoded output with initial data and backpropagate the error through the architecture to update the weights of network. Moving on to the next architecture, GANs. The GANs are a clever way of training a generative model by framing the problem as a supervised learning problem with two submodels. The generator model that we train to generate new examples and a discriminator model that tries to classify examples as either real or fake. The two models are trained together until the discriminator model is fooled about half the time. Moving on to the next, autoregressive models. Autoregressive models sequentially generates one pixel at a time in an image along the two spatial dimensions. The pixel of interest I in red is defined by all the previous pixels which are highlighted in blue. Now let's see how we can evaluate the performances of different models.
So autoregressive models directly optimize negative log likelihood while training on the dataset. Here the objective itself provides a good evaluation metric. Hence, we can measure their performance using bits per dim, which is NNL, or the negative log likelihood divided by number of pixels into channels. But on the other hand, the GANs model an implicit distribution. Hence, we cannot use the above metrics, and using handcrafted metrics such as inception score and FID becomes necessary to test their performances. Now, thus we will compare the performance of pixel RNN, pixel CNN and VAE over different datasets, and will separately compare the performance of GANs over the same datasets. So here are the performance of different models on the Cypher 10 dataset. The models Pixel CNN, Pixel RNN and variational autoencoders have the following bits per dim, or the negative log likelihood divided by number of pixels into number of channels, which is 3 in the case of RGB Cypher 10 dataset. Here we can see the VAEs perform better than Pixel CNN and Pixel RNN. Next. The performance of GAN on different datasets can be seen as follows. Here, lower FID scores means better performance of the model over the given dataset. Here, the model performs significantly better on abstract art gallery as compared to the Cypher 10 dataset. Hence, the use of GANs to generate complex images just by training on a handful of datasets can be proved through these results.
Let's look at different models at a glance. Autoregressive models are insufficient during sampling, whereas generative adversarial networks provide the sharpest images. Variational autoencoders produce blurry outputs due to RMSE being used as a reconstruction loss. Autoregressive models provide simple but stable training process, whereas the training is difficult to optimize due to unstable training process in case of GANs. Variational autoencoders use propagation for training. We can conclude our project by saying that GANs produce high quality and high resolution images, though it couldn't capture the diversity in the distribution. Pixel CNN is computationally efficient, but it fails to generate realistic images as optimizing NNL cannot generate visual quality. Quality in case of VAE is poor because they may generate blurred images compared to GANs because of injected noise and imperfect reconstruction. GANs have evolved to be used for a number of real-world uses such as image-to-image translation, text-to-image translation, etc. Thank you. Here's a look at our team.